In this video, we want to briefly derive the parallel axis theorem. We're going to use that in future videos, so let's just take a couple of minutes and see how it comes about. Remember that the playlist for all the videos is at the website digital-university.org. Now, here we have an object, and here's its center of mass. It's comprised of a series of particles, say, each designated as mi. And here we have a point O. And let's say that we want to determine the moment of inertia with respect to point O for the entire object. So, by using the definition of moment of inertia, specifically with respect now to point O, that will equal the position vector for each particle mi from point O. Of course, it's that squared times the mass of each particle mi. And we have to add all of these up for all of the discrete particles that we imagine to comprise the entire object. Now, and that's the moment of inertia with respect to point O. When we say with respect to point O, what that means then is that all of the position vectors for all of the discrete objects originate here at point O. Now, notice that the way we have this set up, this position vector Ri, here is the center of mass. Let's say it's at a distance d, or has a position vector d from point O. Then we can imagine another position vector going from the center of mass to each particle mi. We'll call that Ri prime. So notice that this position vector Ri, well, notice of course that this, the dot product of this, is Ri squared, that term here. But now notice that Ri can be written as the sum of this vector plus this vector. So Ri equals vector d plus Ri prime. D, of course, is just the position or the distance of the center of mass from this point O, and it's point O that we are taking the moment of inertia of. So it'd be as if we had an axis going right through point O. But now, let's consider our formula where for Ri we have this substituted. So now we will have IO, the moment of inertia of about point O, will equal the sum over I of mi Ri squared. Ri squared is the dot product of Ri dot Ri, or we can write it like this then. Here's Ri, so we would have d plus Ri prime, and take the dot product of it with d plus Ri prime. Ri dot Ri is Ri squared, and that's what we have in our formula. So let's see what kind of an expression this gives. First we have mi times the whole thing. Here we have d dot d, that's just d squared, times the sum of mi, that's the total mass. So this is just simply the total mass, big M, times d squared. That comes from this dot this, and then summing over all the mi's, which gives us the big M, the total mass of the system. Then we will also have Ri prime dot Ri prime, that's Ri prime squared, times each mi, so that'll be plus mi, and this is just going to be Ri prime squared summed over I. Then we have the cross terms. We have this dot this plus this dot this times mi. For now, let's just ignore the mi and let's just consider what the cross terms are. We have d dot Ri prime, same thing here. So for the cross terms, we have, we can write it like this, plus 2 d dot, we'll put the m in, mi Ri prime summed over I. So this is the moment of inertia with respect to point O. Let's make certain we did it correctly. So we had vector d dot vector d, that's d squared, summed over mi, that's going to be the total mass. So we have that. Then we have this dot this, that's Ri prime squared, times mi. So we have mi Ri squared summed over I. Then we have the cross terms, and they're the same. This dot this plus this dot this. So we have d. D is just the distance of the center of mass from point O. It's not summed over any I, so we can take it out of the summation. So we have 2d dot mi Ri prime, like this. But we've dealt with this now in video 19a. This is 0. Because what this is right here is, this is summing all of the moments about the center of mass. Ri prime, that's the position vector from the center of mass to mi. Or the position of the center of mass to this one, to this one, to this one, and adding them all up. Well, as we saw in video 19a, and as we discussed in the last video, 19c, all of the moments, when you add all of the moments up above the center of mass, they add up to 0. And again, we proved that specifically in video 19a. So this term is 0. So we have then that the moment of inertia with respect to point O is this term plus this term. Now, here we have mi Ri prime, this radius vector squared. Well, this is just the moment of inertia with respect to the center of mass. Remember, moment of inertia always involved a position vector, its magnitude squared, times the magnitude of the mass. Well, here, the position vector is starting at the center of mass and going to this. And we have that magnitude squared. So this is the magnitude about the center of mass. Now don't confuse this term with this term. This is the simply the magnitude of this vector. Here, these are vector quantities. These are moments right here. And as we showed in video 19a, all the moments about the center of mass add up to 0. So, finally what we have then is that if we have an object, and if we know its moment of inertia about the center of mass, if we know that, then we can determine the moment of inertia at any other point, say point O. It's just simply the moment of inertia about the center of mass plus the total mass of the object times the distance from the center of mass squared. Point O is at a distance d from the center of mass. So the moment of inertia about this point equals the moment of inertia of the object about the center of mass plus the total mass of the object times that distance squared. And that is the parallel axis theorem. And we will use this a lot in future videos. So it's a simple enough thing to prove, but we just want to take a couple of minutes and make certain that we're on firm territory here. Okay, in the next video we'll talk about rotational kinetic energy, and then we have some videos coming up on conical pendulums, and then starting at about video 30 we're going to talk about the motion of a billiard ball. Can it go forward? Can it skid forward, then go into pure roll? Can it skid forward and then come backwards in pure roll? It's actually quite a complicated system to analyze. When we do analyze it, we're going to make use of a lot of the concepts that we derived here in videos 19a, b, c, and also here in video 19d.